Today's lecture will be on DFA minimization. So why we need DFA minimization? Here our motive will be to reduce the number of states that we need to make the make that machine or finite machine to work in minimal amount of time. If this number of states can be reduced, so then the execution time will obviously reduce. Now we will see two different procedures available for DFA minimization. First is called Equivalence Theorem, and the algorithm is being displayed here. So I am just reading it out. After that, when we visit an example, the concept will be much more clearer. Fine. So in this algorithm, input will be obviously a DFA or deterministic finite automaton, and output will be a minimized DFA. Means our motive will be, if possible, we will reduce the number of states that were there in DFA, and the number of states that we will generate in minimized DFA should be lesser than that. Okay. Step 1 says draw a table for all pairs of states Qi, Qj not necessarily connected directly. Means there are, in DFA there will be several number of states. They are generally depicted with Q, and this we will draw a table, and there we will keep all the states there, and afterwards we will mark them according to some rules. We will see that, but beforehand we will write all those states available, and they may not be directly connected, they may be directly connected, whatever may be the thing. Step 2 says consider every state pair Qi, Qj in the DFA where Qi belongs to F and Qj does not belongs to F, or vice versa, and mark them. Means what we are doing here, we are marking those states where, or those pair of states where one of the state belongs to final state and one of the state does not belongs to the final state. So we are marking those pairs where one is a part of final state, another is not a part of final state. Next, step 3 says repeat this step until we cannot mark any more states. Fine. So if we keep on repeating this state until we finishes our job. Then what we will do, if there is an unmarked pair, mark it. If the pair Qia and Qja means we will see the transition of a particular state with respect to a particular input and transition of another state with respect to that particular input, and we will see whether they are matching or not, and will mark accordingly. We will see in the example how to mark it. Then step 4 says combine all the unmarked pairs and make them a single state in the reduced DFA. Fine. So now let us just see an example. Here one DFA is given where there are total 6 states, out of which A, B and F are non-final states, since you can understand they are not marked with double circle, and C, D, E are final states, right? So what our job will be, first we will make a table where we will enter all the states available. Fine. So let us see the step 1. Here what we have done, you can see all the states are written A, B, C, D, E, F in row wise and column wise both, and we have marked few cells with maroon color. Why? Because here you can see there is a combination in row, that is B, and in column A it depicts the pairing between A and B. So if we keep both B cross A and A cross B open, the meaning is same. So we are omitting one part where repetition is, to avoid repetition, right? So here the thing is that A comma B pairing and B comma A pairing are same, because A and B are two states. So whatever the form or whatever the orientation we are using, A comma B or B comma A, the meaning will be same. That's why we have just blocked those cells, nothing else. Fine. Now what is our job? We will mark those states where one state is final and another state is non-final. Means we will mark those pairs. So we have to keep in our mind that Non-final states were, in our example, A, B, F, and final states were C, D, E. Fine. So let us guess where to mark. If we mark the cell B corresponds to A, this will not work because A and B both are non-final states. Next, come to C and A. Is this possible? Yes, this is possible because A is non-final state and C is a final state. So if we proceed in this manner, you will find this one, right, where C and A, one falls under non-final, another falls under final. CB, similar for DA, similar for DB, EA, EB, FC, FD, and FE. Okay, rest will fall under the same category, so we have not unmarked those. Now what step 3 says? Step 3 says if this procedure is completed, means if we are able to mark those pairs where one state falls under final set, another state falls under non-final set, then we are done with this step. Next, what we will do, we will find out if any more pairing can be done using the next step. Let us see what step 3 says. We will try to mark the state pairs with green color check mark transitively. We will see we have used green color check mark in the next slide. If we input 1 to state A, you can try with other states, but it will not possible. Whatever the possible thing is, I have just kept that in my slide. If we input 1 to state A and F, it will go to state C and F respectively. Please consult the diagram or consult the table, whatever is easy to you. If you can see that if we put 1 to state A, it will move to F, and again means we are just trying to make the pairs of those which we have not marked, which are unmarked pairs. We have to see one is BA, one is DC, one is FA, FB. These are unmarked, and two more are there. So what we will do, we will check for all the combination, but here I have just marked those that are possible to make pairs. For others you can check, and you will not you will find out that they cannot be marked using this procedure, right? So let us proceed. If we input 1 to state A and F, it will go to state C and F respectively. Now where it is going, we are putting 1 to if you remember the state that if we put A to QI, and if we put A to QJ, means we are putting the same input symbol to two different states, and we will see to which state they are transiting to, right? So here we are checking with input 1. If we are putting input 1 to state A and F, they will go to C and F respectively. Now we have to check whether C and F are already marked or not. If they are already marked, then we can mark the pair AF. Similarly, if you check for BF, then you will find out that if we put 1 to B, it will move to D, and if we put 1 to F, it will move to F, right? So if DF is marked, we can mark this pair as well. Fine. So let us see what are the new marking we have done. As I stated that we will mark with green color check. So you can see this much ticking can be done. You may check with DC or DC and then EC and ED, whatever the blank spaces are there, you can check. You will find that they cannot be marked with following these conditions. So now what we have to do, we have to make pairs of the unmarked states and the marked states. How to do it? See, after step 3, we got the combination A, B, C, D, C, E, D, E that are unmarked. Means these are the cells where we have failed to make pairs of, right? Now what we will do, see here, if we combine this tree, that is C, D, C, E and D, E, and following the transitivity property, what you can write, it can fall under one category, that is C, D, E. So if we include A, B, C, D and E, what the state in F, right? So this final minimized DFA will contain 3 states, namely F, another is A, B and C, D, E. Now the question is, which state will be our initial state, which state will be our final state. Obviously, if we follow our original diagram or original DFA, A was the initial state and C, D, E were our final states, right? So here obviously A, B, since A is falling in that set, so B will be our initial state, and your C, D, E will be final state. So if you follow the diagram, here should be A comma B, somehow it has been missed, so you can do it. And if you follow the combination, you have to see what A is doing for 0 input, what B is doing for 0 input, and we have to union that two, so we will come back to this one. Again, for one transition for one input, we will see what A is doing for 1, what B is doing for 1, we will make the union of that two and will move accordingly, right? So this is, I think, this is easily understandable. Just follow the previous original DFA and you will be able to mark the transition very easily. Fine. Now this is another method using which DFA can be minimized. This is, as per my knowledge, this is much more famous or easier or efficient rather than Neroid theorem. So what this equivalence theorem says, if x and y are two states in DFA, we can combine these two states into xy if they are not distinguishable. Same thing they are saying, right? If they cannot be distinguished, we will keep it under one set. Means the same thing we have done there. If we can make the pair, we will keep them under one set. If we cannot make the pair, we will separate them, right? So two states are distinguishable if there is at least one string S such that one of the transition, means you can see here x and y are states and we are putting the same input symbol. For that we have to pick up the transition value, and we have to find out what the string they are accepting and what the string they are not accepting. We'll see in our example. Hence DFA is minimal if and only if all the states are distinguishable. If already the DFA is like this, that no states can be distinguished with one another, they are indistinguishable, and then obviously we have to move on. If all of them are easily distinguishable, so that will be minimal DFA. We cannot move, we cannot do anything else. Now let us see the algorithm. What our first step will be? Here our first step will be, we will divide the total number of states available into two portions. One is called final state, another is called non-final state. Here we will mark each state with, means we will follow a iterative pattern. Here we will mark the first stage with P naught. Generally this P naught is, this terminology is very famous because we are partitioning, that's why P is used here. So for the initial state, P naught will be used, and take a counter K and initialize it with 0. Means we are just iterating, nothing else. First we will partition these two into two portions, then we will see how to get on to much more partitions, and keep on doing until and unless two consecutive partitions results in the same value or same result, right? Then step 2 says increment k by 1 for each partition in pk, divide the states in pk into two partitions if they are k distinguishable. It is little more tricky and it is little more difficult to understand until and unless we are moving to example, but for now just concentrate on this. The two states within this partition x and y are k distinguishable if there is an input such that that input mean one state and that input in another state y are k minus 1 distinguishable. We will see how to do that, right? And then I have already told you, if two consecutive partitions are equal, then we will stop there, otherwise we will keep on repeating. Now instead of concentrating on this algorithm, let us move to example. I think that will clear your doubts. Fine. So this is the same diagram as we have seen in our Neroid theorem. Here again 6 states are there, out of which 3 are non-final, 3 are final. Which are non-final? A, B and F, and which are final? C, D and E. So first our job will be to draw a transition table, right? This is done because this will require, you will understand how to why I am saying that this is required. Fine. So now next what we are doing, just focus on P0. I will later on explain how P1 is generating. What P0 is doing, just separating final states and non-final states. What are the final states? C, D, E, and what are the non-final states? A, B, F, right? So we have just separated that in two portions. Now what is our job? We have to find out whether we can whether we can divide these final states among themselves or non-final states among themselves. How to do? So in case of first, I have just written where it is possible. I am just telling you the method, you can check for all. Now let us focus on ABF. If you consult the transition table, you can see that if we put 0 on A, it will move to B. If we put 0 on B, it will move to A. That means for both 0th value or 0 value at A and B, the transition is to a non-final state, right? And if we put 1 at A, it will move to C, and if we put 1 to B, it will move to D. Again, here these two newly generated states, or after transition, they are moving to two states where both of them are final states, right? So they are following the same procedure. Again, I am repeating for your convenience. If we put 0 at A, it will move to B. If we put 0 at B, it will move to A. Both the generated states are non-final. If we put 1 at A, it will move to C. If I put 1 at B, it will move to D, and both the states are final. So both of them are working in the same fashion, right? But in case of F, you will be able to see, if we put 0 at F, it is moving to F, non-final, fine. But if we put 1 at F, it will move to F, it is again non-final. So it is not following the same rule as of A and B. So what we have done in case of partition 1, or for where k value of k is 1, we have just separate A, B, F into A, B and F, right? So just keep on following these steps for others. There no more partitioning is possible. So again P2 is generating the same state, hence P1 and P2 are equivalent. So we have to stop here. So let us see how the transition diagram will look like. It will be like this. Again we have you have to write A comma B in the initial state and follow the same pattern. Oh, another mistake is there. For CD, the self loop will be, I think, of 0. Please mark 0 there. Somehow I have missed it. I'm sorry for that. Right. So I think you will be able to draw this diagram. And the same transition table is been shown. Anyone, if you can draw, if you were able to draw the transition diagram, you can draw this table very easily. The same thing. Fine. So this is the end of today's lecture. In next class, we will learn finite state machines. Thank you.